You don't want that, Steve.
No.
Good evening, everybody. I'm guessing with Steve having been around as long as he has, probably at least as long as me, probably longer. You all know Steve Harvey is our area sales engineer for Grundfos for the Midlands, West Midlands technically. And you've been on that role in that patch now for how many years?
Just after the turn of the century.
Yeah. So Steve's now moving probably to more of a technical support role as they sort of approach your impending.
You mean you're trying to put me out the grass?
Packing it in.
No.
So find that there are other engineers on the patch. There's Dave Priest is out there as well. But Steve, in terms of his technical knowledge and history in the industry, is second to none. So without sort of going on too long, I'll pass you over to Steve, and we can move on.
Thanks, Nigel, for that introduction. I don't know what you want to pay for that, but it won't be a lot. Right. Now, that's bloody typical, but we press the wrong button again. Pick this back up. Let's just close this down. Start it again. Get rid of that. Get rid of that. What's taking up? It was all set up to run, but it went to sleep. Right. As Nigel says, I've been in the industry for quite a while, since 1972, apprenticeship and so forth, and people used to use belt drive and sort of ancient stuff for electronics. It was just a fan in a bucket back in those days. And some of the older ones, you might remember the old gravity systems. None of that nowadays, of course, but there you go. Right, what we're going to talk about tonight, district energy. Water-based district energy, not electrical, for heating and cooling. A lot of people refer to the district heating, but a lot of places do district cooling as well. Okay? We're just on the edge of a district energy centre. I'm not sure if this particular building's attached to it. It was an energy centre over the other side of Harvey Road, where the block of flats, and it runs down through Broad Street and disappears over to Aston University. Various buildings are connected to it. It would be nice if all the buildings are connected to it. If this was Copenhagen, every building would be on it. But in the UK, we're a bit still a little bit sceptical, although district energy has been around since the early 50s at least. So this is nothing new. It's just there's been a more incentive to get in on that game. And I suppose in the broadest terms, in the UK, district energy is more than one building. It could be just two buildings on the same energy centre. So we're still playing at it, whereas in other countries it could be 5 or 6 villages or a whole city, or huge complexes within cities. Right, what we're going to look at. What is it, why it matters, pumps, what you need to consider. This is an important one from the pumping point of view, and various methods of control, which in theory, from my point of view, obviously that bit is the most important, how you do it and what you do. And then at the end, I've preempted a couple of questions maybe that you might ask, but we'll come on to those later. What is it, why it matters? We talk about global warming, running out of energy, the demand on power stations is too high, we've got lights on everywhere unnecessarily, let's say. They want to use energy meters in everybody's house, because energy meters will save you energy. No, it won't. It's only if you use it for what it's meant to do. We're trying to sell it to you for the wrong reason. So this survey was done in 2015 from a global point of view, and the breakdown of where all the energy is used and comes from was something like this. It's probably a little bit steeper now because that was only 3 years ago, so it will only get worse. We might start to reduce some of these bits. What we should be doing is increasing that bit, but also reducing the amount of energy we do use, because there's a lot of wasted energy. old motors, old fans, old lighting systems. A lot of systems are LED now, which are very economical to use. So trying to reduce it and using better energy is all where this comes from. And instead of having, say, 200 houses, each got their own 10, 11 kilowatt boiler or whatever, you have an energy centre, which will probably have less than half of the 200 added together, or a block of flats. It's much more economical. It's just getting your head around how those things work. It's quite easy. The numbers just don't stack up when you first look at it. So don't keep putting margins on margins. Right. We need to rationalise the use of energy, as I mentioned. New technologies, that's an important one. Renewables, particularly. But in a lot of systems, you can't always do that. Because you might have high temperature buildings, 80, 90 degrees C or 110 degrees C on medium temperature. So you can't always use renewables in those sorts of buildings. So you need to develop a system from the front end, i.e. not from the energy sector, from who's actually going to go on it. There's no point in producing an energy centre and chucking out 110 degrees C water if people at the other end can get away with 60 degrees. Things like that. Right. What is it? It's basically a heating or cooling system in a local energy centre or power station, serving a network via distribution pipelines. So we have power plant or boiler houses, or a combination of both in a bigger system. Network of pipes, obviously in the UK they'll be underground. In places like Russia, these things are above ground. I don't know if you've ever seen any films with this stuff above ground. Bit of a problem if they don't have glycol in it. And there is a city or a small town in Russia that didn't put glycol in it. It goes to minus 25. The best temperature is about minus 10. We've all moved out because it's just got one big ice block. All the heating system is solid. And of course, some idiot didn't put glycol in. They can't thaw it out, so we just up and left. Apparently it's still there now, but just a thing to bear in mind, if it is above ground and you get low temperatures, you're going to get problems. So local substations and domestic hot water production. Again, they put everything into the network. Mixing loops in buildings, again, local substations in buildings, like the light. Is anybody here from Coaches? The library, I think that was a Coaches job. There's a substation in there. There's also a chilled water generation plant that sends cooling out to the network going around. So you've got the main heating system and the substation generating more, providing not only that building but other buildings in and around. So it all works together, sharing loads. So it's built up as a network, not in isolation. This is the backbone, or the main source. People use things such as, say, waste heat plants, or energy from waste and that kind of thing, as the main plant. There's one going in Bristol near Avonmouth. There's an old waste plant there. They're using that as a core source of their heat and energy, and pumping it from Avonmouth, which is 8 or 10 miles outside of Bristol, up over the top near Gloucestershire, the border, so people in Gloucestershire can tag onto it, pumping it around into Bristol. They're just choosing which route to go into, and they haven't quite sussed out how to go over the river yet, whether they go under or over, or just across a bridge, that kind of thing. But from a main power plant. In the main power plant, a lot of people generate electricity, and we're using the byproduct, hot water, like a CHP unit. There's one in above the station in the centre of town, energy centre there. You can't actually use it at the moment. Well, it's actually probably in use now. But they couldn't up until recently because they couldn't get rid of waste heat. Because the network was going by, but they couldn't get the flow rate in and out to take the heat away from the generator. So they just couldn't use the electricity from that generator. So as long as it's all set up correctly. And they talk about abroad, like Denmark and places like that, we talk about towns and cities. We talk about a number of buildings, maybe a campus in a university or something like that. Then, of course, if you've got a main heating plant or heat provision, so you've got opportunity to use all these other sources of energy. If you buy the sea, it's sea, wave power, potentially generating electricity, biomass boilers, other CHP variations. This is a problem in London because you can't have that many CHP places within a certain radius because of the emissions. So they're cutting down the number of CHP plant rooms in large cities. All these things have to be taken into consideration. So you could have a combination of gas, biomass, geothermal, some waste incineration, which could even be the main plant, solar, if you've got a big enough area, oil, not that we have many oil wells in the UK, I don't think, and that there is for something that we don't know about. There are people going around the country trying to generate interest from really deep geothermal, where they're talking about going down 4 or 5 kilometres, or 2.5 miles-ish, taking heat and water out, bringing it up through a plate heat exchanger and then sticking it down another one in a different area. So all these projects that people are looking at, crazy sort of money, it will be millions to invest into that. So it's a long-term project. So there's lots of sources of energy to produce heat or cooling that can be used. We tend to look at it more in isolation for a particular building, as opposed to stepping back and looking at developing a housing estate or a future industrial estate as the whole thing. And that's where this stuff really comes into its own. A single building is difficult. Multiple buildings, again, like a university or a hospital, that's ideal for this kind of application. That's a key area. A lot of people don't like using thermal stores. I'm going to use the network as the store. It doesn't work. Put a store in it, it always works. So if you've got 5 or 6 miles of pipework, you think, oh, water goes out hot, comes back cold. When there's no demand, it goes out hot and comes back hot. So you've got CHP and things like difficult control. If you've got a thermal store, it doesn't matter if it comes back too hot, you just turn the CHP off until that completes. And then so thermal store is a key to why these systems work very, very well. Not just the network pipe, even though it might be 600 mil diameter. In the distribution network, it's from a series of insulated pipe. Sometimes single pipe insulated, sometimes double pipes. And there's obviously a network of people who sell this kind of equipment. And there are companies, all they do is just install that kind of stuff from A to B. They join the dots from here to here to here. So flow and return from the main centres into commercial properties, industrial and housing. Now, all of those could have different temperature requirements. One of the problems is people tend to work from an energy centre back here. We can chuck out 95 degrees C, 100 degrees C, whatever. If the industry side wants 110, these might only want 60, which I mentioned earlier on, and these could probably get away with 60 or 70 or whatever. So you've got a mismatch of different temperatures. You can group all these, loads of housing on one part of the network, through a series of plate heat exchangers, so you're working at a lower temperature in that area, and differential temperatures come into play because then it affects the resistance and the flow rates through buildings. Likewise with these, if you need a higher temperature, you can have a lower temperature from here, but put local power just to top it up at the last area where they want it, maybe for a process or something like that. Okay? And this mentions about cooling, same sort of principle, it's just different temperature ranges. And here, in certain countries, we don't insulate the pipework at all, because it's already cold outside. That's the most important thing. Delivering the heat and cooling as cost effectively as possible. So, the heat loss in the pipework versus pumping costs. So if you have a low delta T, you'll end up having high pumping costs. A wide delta T, you've got lower flow rates, therefore lower resistances, therefore lower power motors. So lower costs. And it's nothing to do with your pump's cheaper than his pump, or yours more expensive than his. It's what the running cost is. And this is, in district energy systems, it's the running costs for 25 years, if the pump's last that. But 25 years for, say, a 30 kilowatt pump, that's, particularly around 24/7, can be on many systems. You get the energy wrong because you've chosen the wrong product, even if it's 1 or 2 kilowatts out, 24 hours a day, 365 days a year, 25 years, you can put that out. You're talking thousands and thousands of pounds. It doesn't matter to the installer if he's fitting it and he's off. If you're the ESCO, the company is running the district energy circle, that is important. There are different methods to connect into the system, and that is crucial to whether the system's going to work or not. You can have a direct connection, which is heat in, heat out, just like radiators. But this could be different separate buildings, just valved off. You could have indirect via a heat exchanger, so you're hydraulically separated, or indirect via a mixing loop. Each have got their own benefits, except the first one, other than being cheap. Because if you've got an energy centre down the bottom of the valley and a block of flats on the hill, the static height in that system could be huge. It could be, say, 30 or 40 metres. That's 4 bar pressure before you start talking pumping pressure. And if it's sort of a hell of a way away, 90 metres in the air, that's nearly 9 bar pressure acting in the plant before you even start. So that isn't a good idea. It's cheap, it's very difficult to control, and for big systems, a no-no. Now, Warwick University and Birmingham University used to have a mixture of all of these. We've gone away from that wherever possible because you can't get decent control. Local control is a no-no. It's, if you've got some honking great pumps moving the water down the line, these line of resistance, you've got to screw these down. It's a nightmare to balance and control. Via a heat exchanger, it's brilliant because we could be on the top of a hill with 40-storey building. So our building could be at 10, 15 bar pressure, whatever. But this lot, the energy centre, could be way down south. So you haven't got boilers and chillers and other equipment that needs 20 bar, 25 bar rated. Also, this side can be at a high temperature, and this side you just take off the temperature you want. Very good controllability. Yes, it costs more money. You're still going to have pumps in the building, and that plate is the key to it. They're hydraulically separated. You can do what you want this side. Brilliant. And you can control it spot on. I would also, if that's just connected directly to the lines, put some sort of thermal store inside this building. If you've got a very high peak load, you can have a small pump here taking off the flow, filling up your thermal store, and then sub pumps doing all the zones off of it, what you need when you need it. Because the other thing is, if you take it off at, I don't know, 80 degrees, and it comes back at 78 when there's low demand, the people you're buying your energy from are not going to be best pleased. Because you said, I want, you're going to on a 20 degrees difference. So the billing becomes a problem, which is a nightmare in low demand. In other words, block of flats, or 2 or 3 blocks of flats, and there's 3 people moved in. For the first 6 months, that's going to be an absolute nightmare to control. If you've got some sort of thermal store in that area there, it's okay. It doesn't matter coming back to the thermal store at high temperature or low differential. These are just tips, but you've got to have a big area for the thermal store. And how big you need. Indirect via mixing loop, again, good controllability because you can send the water around again. Initial costs are higher than this one because you've got the mixing loop in there. That again, the commissioning could be a nightmare because if you've got high pressures, in some of these systems you can have 700, 800 kPa leaving the plant room, which if you're the first building on that plant room, some of that pressure is going to find it into the first building. So it's going to be a bit of a nightmare to balance out. That by far is the solution. It does work. And of course, if you've got a lower temperature here and you want a higher temperature here, this is where you can put your additional boilers or CHP or whatever into your own little bit. And you said you can chuck in 80 degrees C, but an industry factory might want 120 degrees C or whatever. You can add to it. But the core heat comes from the district. So a lot more flexibility with this one. Yes, it's more money. In the long term, it's cheaper to run, more controllable, energy savings are much easier to do. Okay? It's the long term that district energy is about, district heating schemes or systems coming to their own. What's the potential? Right. That's one key area, but that's all down to do to temperatures again. Surplus heat from waste heat, CHPs, that's where we can get it from. It's better to have a large central plant than lots of little ones. Block of flats, 200 flats, average flat kilowatt rating is whatever, 10 kilowatts, whatever they are. So 200 flats, that's 200 kilowatt boiler, with HRUs in each flat. Probably not much more than 60 or 70 kilowatts. Because the probable demand of all that being on, they'll never all be on. It's probably only about 15% if you look at the Danish method of selecting HRU details. So you get a lot more out of the energy sector. And of course, this is the key area, the consumer diversity. Here you might have a school, factory, other bits and pieces, with residential areas. So that lot's not going to take a peak demand at the same time these are, and same with those here and here. So one energy centre up here can feed all of these at different times of the day. You don't need masses of power. You can cater for a peak load by having a thermal store. But the bulk of the time, you don't need it. And we're all interested in CO2 emissions. Still can't get my head around that. And that's the main thing, more monitoring and control. So you know what's doing, what's going where, and you can control the pumps better. At the end of the day, a pump is a fan in a bucket. I get that in every presentation. It is literally a fan in a bucket. The impeller is the fan, the motor just stirs it around, and it goes down the pipes. You speed it up, slow it down. The key is how you speed it up, slow it down to interact within the system. Not rocket science. District energy, I mentioned earlier on, it's been around for donkey's years, really. I think early 50s, probably late 40s, probably late 40s, early 50s. These numbers are probably a little bit out of date. It was sourced from this area here, not by me. Typical district energy areas. We have got some in the UK. And they're where they currently are. Ones that are actually operating. There's lots of them in the London area, but they're all little ones. Aberdeen, Edinburgh, these guys up here, they love them, particularly communities, little villages here, there and everywhere. Bit of ground source heat, some solar, some wind power, goes to all the outlying buildings, they have a thermal store again, and they all tack into it. It doesn't go outside their little community, but it might go 10, 15 miles down the road for various people. Putting the network in is the expensive bit, running it, not a problem. Bristol is one going in there now. Southampton one's just been put in there. Bath is one we're looking at. Obviously, most hospitals, a lot of them got them already. Coventry, there's one in there where they shot themselves in the foot, where they're trying to bill people. One of the biggest problems in the UK is the way people perceive the billing. Because on the continent, you're only allowed to make a certain amount of money out of district energy, supplying it to a domestic consumer. We're all sceptical of this in the UK. We sign up to be on a district energy, we're going to think, sign up to that, all the eggs in one basket, literally, and that's the price. I'm not allowed to do that. They can make profit, but only a realistic profit. They make the money when they source all the energy from. So it's one different. And the people who install it are the people who run it, not like here, over the road doing another job. And that's one of the biggest issues. So it's quite a few areas. The black spot is around about there somewhere, which is, oh God, I mentioned the name, I want myself, Mansfield. They have had a district heating scheme for years, 40 years, I believe. They're dismantling it because they didn't maintain it. They're putting everybody off the district heating scheme. While the government trying to get people to go onto a district heating scheme or look at it and invest in it, they're going the opposite way because the network's falling apart. It's leaking everywhere. They didn't maintain it. If they did, it wouldn't cost them, I think there's about 6,500 houses got individual boilers. So the energy consumption in that area has just gone through the roof, as opposed to energy centres with probable demand usage lots more. I think it's like a fund in one down here, possibly. Yeah. moving on. So I mentioned the government trying to get people to invest in it. They put money into schemes, and they're doing seminars all over the country. Various people I've been working with the Danish embassy, doing presentations all over the place, Scotland, Bristol, London, wherever, to get people interested about district energy. It's been around for years. It's just the willingness to look at it. It would take off if planning permission was, I won't say automatically granted if you're looking at an energy system, but it would take off a lot more easier if when you get points for planning permission and so forth, if you're going to take part in an energy centre, in a district energy scheme. It would help get, particularly builders, put provision in for district energy. When they're digging the roads up and laying the outline of an industrial unit or a domestic housing estate, for example, if they put the network in for the pipe work, at that stage it'd be a damn sight cheaper to get the network up and running and quicker. So, pumps in the network, where are they? State being obvious, really, I suppose. You've got your main power plant, there's main distribution pumps, filtration pumps, water treatment pumps, chemical dosing and so forth. Then you've got maybe another boiler house somewhere or other, shunt pumps, low temperature heating pumps there, economiser pumps, flue gas, getting the heat back up for flues. And then you get out into substations where, in our language, this is a sealed system pressurisation set type of pump equipment. More distribution pumps sending it around different legs of the network. And then the customer, you've maybe got plate heat exchangers if you've got a well thought out system. And then you've got mixing loops with each building. And maybe each floor, depends how big the building is. Some people just have one pump sending it around the whole building. Some people have loads of floors, different height buildings, whatever. A typical setup, instead of having your main header, heat exchanger as your main loop for the system. So there's quite a few areas from a network point of view, if you're looking at a whole network where pumps would go in. And all of those, if they're selected wrong, just waste energy pumping. That's a typical breakdown of pump life cycle costing. The installer is probably more interested in the purchase price. The ESCO, or the guy who's running the energy centre, is interested in that bit. And that bit. Not really that bit. So over 25 years, we could be looking at £1,000 to build some of these pumps. You oversize it, get it wrong, that could be 40 or 50,000 pounds. If the pumps are set up wrong, I've been to a lot of sites where the pumps have been set up wrong, been running on maximum, and they've been using 3, maybe 4 times the energy we should have done. There's one over near you, Glenn. It was a centre. Somebody put them all onto maximum. All pumps were running, duty and standby pumps, and wouldn't turn off because they didn't understand how to set them up. Somebody had been playing with the buttons and left them flat out. Commissioning issue or operator error, let's say. But easy to correct. This bit you should understand a little bit more about, I suppose, really. Power in, power out, simple relationship between the energy in and energy out. That's all that refers to. If basic water is based on, most pump manufacturers' curves are based on 20 degrees C. You've got to work on something. So all the curves are drawn at 20 degrees C. You change slightly if you lower the temperature, add glycol, or run it at a higher temperature. It tweaks the power consumption in the curve ever so slightly. So never select a pump right upon the curve. There's always a room for a bit of a tolerance. But that's the basic calculation for doing a water horsepower. How much pumping power do I want? That simple formula there will roughly say it's going to be 1 kilowatt or 101 kilowatt. So you know roughly at the front end when you just outline an overall project, what sort of levels of power you're going to be looking at. It's the pump efficiency that makes the difference between like water horsepower and so forth, and what you actually put in and what you actually get out. And on a pump performance curve, I'm sure you're all familiar with, the curve for efficiency is something like that. And the highest point is the best efficiency, which is important to remember, because that value is used in another question that someone should ask later on, but you might ask it slightly different. Typical pump performance curve, that's the curve, the flow. There's a typical system characteristic curve. That's the power curve, and that's the efficiency curve. So at that point there, the best efficiency point, that's how it will look on the system. If we change certain parameters, like changing the speed, we reduce the power consumption, we reduce the speed, we reduce the flow. Or conversely, if that was using 1 kilowatt and we double the speed, that would be 8 times the power. Okay? Fan pumps, which you all should be familiar with, I would imagine, somewhere on the line. It's the same for pumps, it's just got water in it, really. So I'm not going to bore you with all the calculations there because there's no need. It just shows, if you want a copy of these slides, I think they might actually be on the CIBSE website. I think it's on there, is it? Okay. Sorry? Regional. Also, by slowing the pump down, the efficiency adjusts as well. So you're not losing a lot of efficiency, you are reducing the power consumption considerably. But the efficiency stays reasonably good as a percentage. Percentage efficiency never paid any bills, or you were never charged on a percentage. You were charged on the kilowatt rating. That's what you pay the bill on. A number of people, I've selected pumps from various consultants in this area, where it's a low flow, high head, and it's been in this area of the pump, which means it's in this area of the efficiency curve. 13% efficiency. Geez, it's like a spoon in a cup. But the power is down here, 250 watts. I'm not really bothered. Because if somebody's got a duty, like a half a litre a second at 250 kPa on a heating system, you've got other things to worry about. One could be in the right industry, I don't know. When I started, half a litre a second was like 30 or 40 kPa years ago. The resistances are going through the roof. Because there's all the gubbins and pipe work going in and adding up. Anyway, right. Network considerations. This is an, and it took me ages to get my head around it, maybe because I wasn't paying attention, really. So, typical heating and cooling systems operate between, on flow temperatures, 4 and 10, and 10 and 20 degrees C for cooling. And heating, as low as 55 degrees. Now, people are going to go, rubbish, 55 degrees C. What about your second? We need 55 degrees C as your lowest, so that leaves you 55 degrees. Well, that's in the energy centre. These pipes are so well insulated, the temperature loss over a couple of kilometres is next to nothing. So when it's going into a domestic premises, for example, you're losing either nothing or next to nothing in the way of temperature. What we like to do in the sort of 65 degrees C when you're doing through a plate heat exchanger, all that kind of stuff. So, but on the bigger systems, 80 to 90 or even higher. I did have a heated discussion with a guy from London once. He said, oh, no, you need to be at 110 degrees C. 110 degrees C, straight through to the bone. He went, no, yeah, see what they do. Even that's too hot to touch for any at the time. But you do get paint will be peeling off about 110. Maybe lots of forms to fill in. If you can pick a pen, there's some more stuff. Anyway, right, so what people are trying to do is increase the temperature on cooling and lower the temperature on heating. So if you've got an energy centre chucking out, I don't know, not as low as 55, I don't think, in our world, probably 60 or 80 degrees, 60 to 80 degrees, it's coming back at 40 degrees, you've got a good operating system. It's what's it's going to feed. So really, before you do an energy centre, you want to go to the other end and say, what do you do? Are these radiators, air handling units, fan coils? What is it you actually do? Underfloor heating? You certainly don't need, if it's only underfloor heating, you can get away with 55 degrees, easily, and then bring it down to what, because if this floor was 55 degrees, we'll get the G, wouldn't we? It's too bloody hot. So what benefits have we got by lowering the temperatures? Reduced heat loss. So you've got a 10% loss over 5 or 6 miles, you've only got 10% of a small value, I suppose. You can put more in, you can get more out of the CHP and serve more people, because you've got higher values here you can put into a district, into a thermal store, and then more people can have access to lower temperatures. Better efficiency if it's a heat-only plant. You can then, if you're talking lower temperatures, add more renewables, like solar, ground source. things like that, heat pumps and stuff. Reduction of CO2 emissions. I don't know how you really prove that, to be honest. But there you go. Lower return temperatures improve efficiency in some generation plants in heat pumps. Yeah, okay. So wider the gap makes the overall efficiency better. If you have lower system temperatures, you lose less heat, I suppose. Right, rework that. If you have a lower differential temperature, I've got that, read it this morning, this stuff. Lower differential means a higher flow temperature, flow pressure, higher flow in volume, which means a higher resistance. Okay, so you need more pumping power. If you've got a higher delta T, there's a wider gap, 30 degrees, 40 degrees, you've got a lower flow rate. If you've got a lower flow rate, you should have lower resistance, which means a smaller pump, less energy. What tends to happen is, in the old days, it was an 11-degree drop, did 10 litres a second. Now it's a 20-degree drop. So it should be roughly half the flow rate, and the resistance should come through the floor. What's actually happening with it? That was the system curve working here. Now it's like that. You work up there, because you've got smaller pipe works, and the resistance is gone. If you use the same size pipe work, you work down there, much smaller pipe. If you're digging a hole to bury the pipe, it's the same size hole, usually. On this one here, you might end up having a higher flow temperature with a wider delta T, like 80-40 or 80-60, something like that. You could end up with a higher. So if your system's not well insulated, you could lose a higher proportion of your temperature. So it's a bit of a balance. That's on the design and installation side. These are things that we picked up on over the years. But if you keep the delta T as high as possible, you reduce your flow rate, reduce your resistance, and therefore reduce your pumping cost. It's a smaller pump, which for likes of me and Nigel is not very good use, is it, Nigel?
No.
You want bigger pumps. And if I was paid on commission, you want huge pumps. But smaller pumps makes this easier to control. You oversize on a district energy system, you won't get your return temperatures right. When there's low demand, you will have loads of problems. So, low differential temperature equals high flow, high pressure losses, and high distribution costs. Which, in theory, if we increase the flow by 33%, 77% increase in pressure, and 135% increase in power required. So, narrow the band, bigger motors to push on, and you've got less control. We've done this in a little graph here, showing 3 different temperature differentials, 5.6, 6.7, 8.3. The blue one here requires more pressure at the pump to get the similar sort of pressure out in the system. We're pushing more water down the line to maintain a narrower temperature range. So you've got greater pressure distribution diagram through it. At the lowest one, the widest differential, we can start off with a lot less pressure at the pump. Oops, putting that back now. A lot less pressure at the pump, and a lot less pressure throughout the system to achieve the same differential out at the circuit. Keep the pipe resistances up and the valve sizes up. It costs to get more money, but 25 years or more of these things, in district energy still could be even 40 years. So you're talking about a right arm and a leg to run some of the shows. So basically, the higher delta T, the lower the need for differential pressure in the system. So you're not getting such a high differential pressure. So buildings on the early part of the circuit are seeing a higher rise or fall in pressure as you go down the circuit. So if you've got less losses, you've got a smaller pressure differential as you go down the street. You disagree or agree with that? Just unusually completely. But it's a pressure distribution diagram, done with different things. On the first story floor. Here's a typical block of flats, very similar to what we've got out the back here, on the other side of Harvey Road. Energy centre, pumping out to 3 different blocks. As you go down the line, the first one, this could be 100 kPa, then you get into 70 kPa, here 42, whatever, at the very end 14. Actually, in fact, they were feeding HRU units, and you need something like 50 kPa at the furthest HRU. They were actually pumping into the building, so that was going from here all the way down here up to the top floor to the end unit, needing 50 kPa. So that value there needed to be at least 50 kPa more, but to achieve that, this needed to be 250 kPa, thereabouts. There are different ways and means of doing that. You can have a smaller pressure pump doing all of the flow here, another pump here doing the pressure for this section, but the flow for the whole lot, and here, a pump for that section only, so that would do that bit there. So the pressures would come down. So you're not getting imbalance within the circuit, particularly if certain blocks close down. That pressure wants to try to go somewhere else. And of course, smaller pumps, smaller running costs, and you're not having a holding great pump, which is difficult to work on. You might end up having smaller pumps, which all man can work on quite easily. But there are different ways and means of doing that as well, which I'll come to. Delta T, again, versus power with the power. Sorry, differential 5, 6, 7, 8, 9, 10 degrees. Same with heating, 17, 20, 23. This is to relate to power, the hydraulic power. If we had 100 at 100, that's the flow rate and the percentage. With a 60 degree differential and a 20 degree differential, by changing it by 1 degree in a 3 degrees in a heating system, the power is reduced by 27 by just changing 1 degree or 3 degrees, depending on the circuit you're working on. That's the sort of impact you can have by moving it further and further, stretching that envelope a little bit. The wider the difference, or the difference in, instead of working that kind of power, you're down here. If we move more and more now down here, you'd end up adding a considerable more reduction. So that's 173. So 27 is that the difference between those two. If you went down to here, obviously, that's a 60% potential reduction in consumption. We can't influence that. We can only recommend, consider these sorts of things, and then when you've calculated out your duties and bits and pieces, what you want to do, we as pump manufacturers would recommend this pump, that pump, or combinations of pump and suitable method of control. This bit's important. How do we do it? The biggest problem, which I think most people understand, there's no constant load in a system. In a particular circuit, there might be a constant load, but in an overall system, there's never a full load all the time, over 24-hour period. It does vary. And throughout the year, you might only want 100% load. I'm sure you've all seen this for even ordinary heating systems. You only want 100% load for a very, very short period of time, 2-3 days of the year maybe. So you get away with a much smaller plant. You normally put size your pump on the maximum duty of the system. So in an ideal world, you'd select a pump there. What tends to happen sometimes, because the flow is relatively low, you end up working up there. You've got no control over anything anyway. But it should be out here somewhere. Ideally, in that sort of area of a pump, slightly over this way is ideal, because as you slow the pump down, you're still maintaining relatively high efficiency. If you're in this area, you're down the efficiency side, okay, you're still using relatively low power, but you haven't got as much control. And the other thing to bear in mind is, something I'll come on to later on. You can't always select a pump to work in that area, because you might have half a metre a second at 250 kPa. And the 32 mil pump, at that kind of duty, will do something in the 3.5 litres a second maybe. So if you only got half a litre a second, you're going to get a duty up there somewhere. So your efficiency percentage goes out the window. So in your specification, you can't put, I want an 80% efficient, overall efficient pump. Be good luck with that. 70 to 73% is about the best you ever get. And that's what we see in this area here. If you stick an inverter on it, it's less efficient. Running at 100%. So many people running a pump, 100% speed, with an inverter on it. What a crap. Wasted time. The inverter comes into its own when you have situations like this. Normally, in the old days, which wasn't that long ago, fixed speed pump would work there. Your actual flow rate is here. So you screw a valve shut and it works up there. In reality, you should slow the pump right down to that point there, like that, and then work there. Brilliant. So you've saved all that energy. But being a variable speed pump, the efficiency doesn't change that much, unlike a fixed speed pump. The efficiency goes from there to there, the power only goes from there to there. Variable speed goes from there way down here. The efficiency stays pretty good until you get to really low flows. So variable speed is ideal. Never select on the line and hope to run it on the line because you're just wasting your time. The only advantage is you might have some electronic connectivity that you can extract information. And that's the only use you've got. So you also have lower head. And of course, if you oversize it, you can wind it down. Or if you allow it, you can always wind it for future use as well, of course. So better efficient, less power. This one refers to you've seen this a bit earlier on in all the calculations that it just refers to, by changing the speed to reduce it by 50% results in 87.5% reduction in reach. Which, if your system characteristic never changed, and you're working from there to there, based on delta T, temperature, which is the best way to do it, but we all do it with 2 valves usually, that is the biggest energy saving because the pump is slowing down so much and reducing in power so much. The energy saved can be lost if you get it wrong. Right. These methods of control are standard terms within the industry. Constant pressure. Constant pressure is used a lot, but it's only constant pressure at the point of measurement. In this particular example, it's across the pump. So the pump maintains, let's say, for example, 100 kPa at maximum flow or minimum flow. Brilliant. The valve closes, the system curve goes up and down like that. The pump just maintains a constant pressure at the pump. Or if you're measuring across the manifold, with a couple of pumps on, across that manifold. Yeah, that's all right. It works to a degree. It doesn't give you that much in the way of energy saving. It gives you a little bit of control, but not a huge amount. You do save some energy when it slows down. It's okay where most of the resistance is in your control valves, not in the pipe, long runs of pipe. If you've got long runs of pipe, but you don't use that method. You shouldn't really use that method. Calculated proportion pressure is where it's built into the pump, where you might have sensors across the pump, and then the algorithms in the pump say, well, I'm slowing down. If I work on a slope of 50% or 30% or whatever, it works down a line like that. One of our pumps work on 50% standard, and other pumps we can actually alter the slope. That's a greater method of saving energy. And it's also great because you don't have to run miles of pipe cables throughout the building to put your sensors at the furthest point. So it's built into the pump. Or it can be built into a control. That's ideal where most of the resistance is in the distribution pipework. And as long as that point there is getting your minimum flow to the furthest point in the system, that's great. It'll work fine. It's a bit of a compromise, but it works fine. This method, by far, is the best method in measuring pressure. The differential pressure transducer or sensor is out in the system somewhere. And that somewhere, CIBSE recommend 2/3 of the way down the line, no problem. But if you've got HRUs, there's only really one in one single building. The best place is the furthest HRU and the longest one away. No, there's the index. If you've got to maintain 50 kPa up there, that slope, that point down here, virtually no flow, is going to be 50 and a bit kPa. That sensor then goes back to the pump, not via the building BMS, back to the pump, and the pump will maintain constant pressure at the point of measurement. The curve it produces will be up that line there. It could be a straight line, but more often it's slightly bowed. And that is ideal where you've got lots of consumers coming off before the measurement. Because if you know the index circuit's getting it, everybody else has got to get it. Simple. Works every time. Unless, like push or screw, you just need to have a sensor in the other place. Across the manifold. I think the controls guys are working.
Okay, what's like one of the risers then?
If you move this sensor away from the furthest point, you get a rising pressure at the end of the circuit. You still get the decreasing pressure at the pump, so you save energy, and maintain constant pressure at the point measured. So in the 2/3 of the way method, the pressure distribution diagram stays constant in the 2/3 of the way along. It rises at the end, so you get some imbalance, potential imbalance after the sensor, and reduction in pressure before. Whereas if it's at the end unit, you get a reduction in pressure throughout the system. And as long as you've got it in the right spot, brilliant, no problem. On a bigger system, you put multiple sensors in, and poll the results so that they're all meeting the requirement. Because some buildings, it's difficult to know, or complexes, you might have 3 or 4 blocks of buildings, and depending on the usage at the time of day, the pressure may drop a little bit more because there's a bigger demand over there. So you just up the ante a little bit. And if you've got, I don't know, certain pressure snubbing devices, such as a phrase or whoever does them, they'll take out any increase in pressure so you don't get any more water down the line, so you don't get any imbalance. But that is probably by far the best and most economical method running on a differential pressure. It has to be differential pressure, it can't be single point pressure. A number of people put single point pressure at the top of a riser. When it's cold, it's measuring one pressure. When it's hot, it raises another pressure. On it does another pressure. They don't work. You need differential pressure. And where do you put the system? Which is what I just alluded to. The pressure at the pump is still the same. From a selection point of view, if you put it across the pump and maintain constant, if you put it out in the system, depending on where it is, you'll get constant pressure there, all there. You'll get the greater reduction in energy because this pressure here will plummet down. The bigger the speed reduction, the greater the energy saving. Or you've got to make sure the sub-circuits don't drop below their required pressure. Because if it drops below what they are, that's not the index circuit. Maybe that one is. Or you can put on multiple buildings different sensors and feed it back to the BMS, and then they go, oh, hang on, that one's a bit light. Raise it. Pump duty. The selection of the pump is still the same duty, 250 kPa and 50 litres a second, but how it controls depends on where and what you're doing with the sensors. Now, if we look at the network, to maintain a delta P differential pressure, there, that one, it's a bit too small to see in my glass. But we've got a table here. So load 5, fortunately it's way bigger, we need to maintain that value there. 100% flow, it does that, 75 and so forth, all the same way. Now, because of the way this network is laid out, that one goes off up here, this one goes a short one there, and a little short one there, you do get variations in pressure over and above what the full load of the system can take. So that one there, load 3, where's load 3? 1, 2. That one, oops. That one there, that's going to see an increase in pressure slightly as these ones come down and you reduce the flow. So you're still going to get increases and decreases in pressure, but then your differential bypass valves or whatever you got in the system will compensate for that. So you're not pushing more water down those inadvertently. If you just got ordinary red valves with a hole that big, at 1 bar it'll pass, I don't know, 2 litres a second, 2 bar it'll pass 4 litres a second. So you need pressure differential bypass valve top of range, etc. On something like this. These could have plate heat exchangers here with their own little circuits, but if you have a central pumping station, this sort of thing can happen. And the increase in pressure at the pump, we can lose up to 44%, but on the local one, it could be as much as 58% increase in pressure. Okay, is that reasonably clear? My first time just glazed over. I still do. Looking through these glasses, you glaze over. Parallel pumping. This is important. You never use it. You've got a big duty. Don't use one pump. It works. You get much better control with multiple pumps. They can work out Again, variable speed control. So all pumps are being used. This is shown measuring out in the station, out in the system. So one pump comes on, speeds up. When we get up to this area here, we'd start the second pump, so you have multiple pumps running at lower than 100%. Because one pump running flat out is usually more expensive than two pumps running at part low, at certain parts of the pump performance group. Okay? And it's also important, this pit is also important for another reason, which I'll come on to in a minute. So multiple pumping, people think, oh, yeah, I only want duty standby. Yeah, if you've got a duty of 3, 4, 5 meters a second, maybe that's okay. When you're talking 20, 30, 40, 50 meters a second, you've really got to consider, well, it's not an option, you've just got to use multiple pumping. I mean, Nigel's building one, it's got, how many pumps has it got now? It's 130 kilowatts?
132, yeah.
That's the system.
Leeds districts.
Yeah. So they're spreading that over 132 kilowatt pumps each.
And a jockey.
Oh, and a jockey, yeah. Because the nature of the maximum duty and the minimum duty, it's too wide, you end up having about 10 pumps all the same to do it. So you've got to put a jockey in that instance. And when you're down here, a lot of pumps can work down in this area, but when you're down middle of the night, middle of June, no demand, water's going out 82 degrees C, it's come back 81.5. It's so well insulated, nobody's using anything, you've still got to have the water going out. And you don't put a bypass around the pump. Please don't put bypasses around the pumps. It's cheaper. Dumbest thing. Because what happens when Mrs. Miggins gets in the shower at the end of the loop and turns it on, she's got 120 gallons of water by the time you get hot water all the way around the system. You're best having an HIU system, a bleed through to keep the plates hot, so someone opens up things hot water. Anyway, I digress. Right. So speed control pumps connected in parallel. Here's one big pump working in the efficiency area, and its duty point roughly. If you've got two pumps in, we can get a lower closed valve head pump possibly. So this one pump, two pumps, we can still maintain relatively good percentage efficiency, which means lower absorbed power. And when we get the duty to this area, we've only got one pump in. Okay? So if that was one 30 kilowatt pump, it's currently two 15 kilowatt pumps with a third standby 15 kilowatt pump, as opposed to a standby 30 kilowatt pump. So 3 15s might be cheaper than 2 30s. It'd be physically smaller, and one person could probably work on it if it needed to be serviced as well. Well, that's just. Thinking of a pump as just a fan in a bucket, which I mentioned earlier on, really is the wrong way to do it. You do need intelligent information. What's the power absorbed? What's happening about the bearings? What's happening about temperature within the pump? Hours run, fault conditions and things like that. All of those can be built into electronic pumps. I mean, a lot of you see our TPE and the Magna ranges, all of this information is on the screen or can be extracted by backnet modbus, which is the normal sort of stuff nowadays. A lot of people still put volt-free contacts to start, stop, a fault condition, and obviously power, and then they put a backnet card on it to actually monitor what's going on, when everything could be driven through the backnet card. I think people are not quite 100% happy with the network SCADA system. We'd like to have the old hardwire system still a little bit, but you can do both. So on larger pumps, you probably have a separately mounted inverter. On smaller pumps up to about 22 kilowatts, you've got the option of it built onto it from all manufacturers usually. As is the best of course, whatever its composition. The information you can get, work history, work log, duty point over time. You've sized the pump to do X against Y duty, and when you look at the screen here, it's actually working up there. You said it was designed for a job down here, maybe. I've seen them where they've been working here. They've never been up there. So talk about oversized. So when you come to do a replacement or another job the same, you know damn well you're never going to be up there. Oops, never going to be up there. You could be end up down there. And there's the information on the screen to see, to prove that you know, like probable demands on booster systems, for example. It used to be booster set that big. Then it was BS67000, it's that big. Now it's EN803, it's that big. Bit Boolean. But everything's come down and down and down. Less water's used all the time. The heat emitters got better. Right, key learning points. We've only got a few slides left, so keep it away. District energy systems offer improved efficiency. Yeah, so a bigger centre to serve a wider area is better than individual boards all over the place. Probable demand scenario. If you've got 200 HRU units or 500 HRU units, there's not a huge difference in the boiler plant needing to feed that. If you had individual boilers over the place, you had all that, it's colossal amount of energy. So it's better to go for a district one wherever possible. I know a lot of the times you're only working in one building. If you're building onto a new estate, a new industrial estate, for example, where blocks of flats are going up, think energy. That's the safest way forward, really. Pumps aren't always the main energy consumer. They are if you get it wrong. But if you don't get them right, they cause problems, oversized, you can't slow it down enough, return temperatures too close, you get problems with your billing because you're over pumping, too high pressures and so forth. Do you lower the differential temperatures or increase the differential temperature on heating and lower the actual operating temperatures on heating and raise it on cooling? Do you really need to go down to 6 degrees? Or can you have 620, something like that? Increasing the delta T will decrease your flow rate, as we said earlier, which decreases your pumping costs. Variable heat demand, that control is essential. Get that right. If you monitor it, you can do that quite easily. You can either do it via your BMS, or some manufacturers have their own controllers to do it themselves, and then can feed that information back to the BMS. Some manufacturers are looking at cloud-based monitoring systems, as we are. We're sort of pioneering that at the moment. So that if you wanted to look at your stuff from home, you can change. In theory, I could change our booster setting in the factory, log on, pull the data on there, and change all the duty and the parameters, and even commission the booster set from the electronics from the laptop remotely, if they remember to turn it on back at the factory. Basically, I've got to ensure we're talking to somebody who knows what we're talking about with pumps. It's not just a case of give us a duty. Some of you have set your duties and I'll end up, why are you doing that? Why are you doing that? Have you thought about this sometimes? It's not just, I had one the other day, 0.05 litres a second, I think it was 160 kPa. That immediately went, what the f? But because computer says that's what they need. You don't get put to do those sorts of duties. 0.05, that's like less than a glass of water. Just because they could, in the end, they swallowed it into the job. Because when I was showing the pump performance curve, it was so left of curve. It was you couldn't control it anymore. You couldn't measure it. 0.05 litres a second. You know the best way to commission radiators is you turn the heating on, you feel the radiator. Is it hot? Yeah. Well, I know. Job. Can you hear the water going through the radiator? Nope. That's it. Job. What, 3 decimal places on this? Anyway, questions? You've had time to think. Those who are still awake. Right, one of the questions that I get asked a lot is a rubbish question. What's the slowest, speediest pump? What is your slowest, speediest pump? Stop. Turn on. What's your turn down ratio? You want to know that? We do with you. Why do you want to know that? What you want to know is what's the minimum flow your pump can handle. That's the question you should be asking. So I'll go back to you straight away and say, what's the minimum flow of your system? Doesn't go down. Flow. So you'll have a duty, 10 litres a second, 50 kPa, 10 litres a second, 600 kPa, whatever it is. What's your minimum flow on a variable volume system? Work that out, and I can say whether one pump or more pumps are more suitable. The reason being, all centrifugal pumps, mechanically sealed, driven by an electric motor, TEFC, total enclosed fan cooled motor, have a similar characteristic to this, where there's a curve that nobody produces, and I didn't produce this. And that's radial thrust and vibration loading on centrifugal pumps. And as you can see, as you get to to closed valve head, it seems to rise quite high. So as a general rule of thumb, all pump manufacturers state 10% the best efficiency. As I said earlier on, the best efficiency point is the highest point there, back of those curves. Yeah? So if we try to select a pump with, so if that was your duty somewhere there, you've not got a lot of room to play with. If you want to set a pump where, if 10 litres a second sits about here somewhere, the best efficiency point might be 8 litres a second, so the minimum flow is 0.8 litres a second. Now that might be plenty, it might be adequate, but it might not be. On small circuits with HRUs, all you've got through is a little bleed through, 0.01 or something like that, 0.02, 0.0, 0.02 maybe, just to keep you warm. If you've got 200 there, add them all up, that's your minimum flow, plus a little bit for loss. There's not a lot of water. So going for one big pump, not a good idea, because you won't have your minimum flow. So that's when you need to introduce bypasses at the end of loops, which you're wasting energy then, because the pipe's probably already up to temperature, you're just moving more water, so delta T is going to close up even more. What you want to do is reduce delta T, sorry, increase delta T, increase delta T by reducing the flow. Well, you can't go below 10%, because I've said so. Because if it failed, then we found you're running against a closed valve head, and the knack of the pump, then it wouldn't necessarily be covered by warranty. And that would be the same with all manufacturers. With the exception for Grundfos, when you use their glandless pumps, which I'll come on into in a minute. And so a pump performance curve would look something like this. This is one taken off our product centre. This could be anybody's pump, any manufacturer, just happen to be Grundfos because I've worked there. So this is the best efficiency point here. 27 litres a second, whatever that is, 264 kPa. So therefore, that one will be roughly 2.7 litres a second. Most heating systems I've come across, particularly HRUs, 2.7 is too much. But that pump would do that nicely. It would absorb, but it's not on that one, it would be on the next one. But if I used more than one pump, it's the best efficiency point of two pumps, which now is their some pumps, their some. So that's now reduced from 2 point something now to 1.1. So by going for multi-pumps, I've achieved the maximum demand and the minimum requirement. That's based on constant pressure, obviously. If we were working about measured out in the sticks somewhere, you'd be working down here. And the flow rate can reduce even more. If that was there, that's about 0.7, something like that. So worth bearing in mind, that is an important value that very, very few people calculate when they're asking for a pump. A number of people started cotton on, I want 10 litres a second, 50 litres a second, 60 litres a second, at whatever pressure you want. But I also want to be able to, low demand, middle of June, 3 o'clock in the morning, nobody's using anything, just keep the loop warm, bleed through. It's 2/10 of trouble, so what's your minimum flow? That is an important one. So,
is there an opportunity there, like 250% of doing 1/3, 2/3?
no.
Because
What will happen is, you have one, the one Nigel alluded to has got a jockey on it. Ideally, you could have 2 jockeys, so you're sharing the load. Because one jockey will run throughout the summer until people wake up in the morning and it's not really more water. It's like a cold water booster system. Not many people use jockeys on nowadays, because variable speed pumps do quite a wide range.
yeah.
So multiple pumps, which isn't necessarily more expensive than duty standby. We got to maximum 6, for example, duty assist, standby, whatever. I always make sure the last one can run as well, because it's there, just on it. Same in the heating systems or cooling. What you want to do is get that shaded band, light shaded band, as close as possible to 0 flow.
Yeah, but that's what 1/3, 2/3 might do. Because if you
Yeah.
bring 1/3 in, because it's a smaller pump,
Yeah.
you're going to be able to shift that to the left a bit more than
On massive
50/50.
systems, yes. If this was something like 80 or 100 litres a second, I would seriously consider using a jockey, particularly when you've got next to demand at all. And yeah, peak demand is way, way out here on the scale of things. Well, in the middle of the night, you don't want anything.
You just want to hit it in, don't you?
Yeah, that's right. You just want to keep the pipe warm, really. So yeah, maybe a vertical multi-stage, like one of the booster step pumps, only doing half a litre a second at best efficiency point. So it can go down to 0.05. Sorry, 0.0. 0.05. Yeah, tell us that, yeah. So I can't. So it's just to show as an example. But the beauty of that is, and it says here, who's it? Oh yeah, there it is. Right. So if we use the bigger pump, that one, this is 11 kilowatt pump, 27 litres a second, 2.7 litres a second, minimum flow. Power P1 there is that. Power P1 at the reduced duty, down here, is 4.85 minimum flow. Where it could be, most of it's like, middle of the night, in the sun, whatever, no demand. So if we use the next size up one, we've saved energy at, in this particular example, at peak load we've saved energy, and particularly we've saved energy at P1, at the lower duty, operating there. If we were measuring out in the sticks and we were working down a line down here, that could probably halve that flow rate and greatly reduce the energy consumption and the minimum flow, which is what we're doing at Virtual Street. Very similar to that. You're using the furthest HIU, I think, are you? Yeah. So that's coming back. So you'll have a slope, but is it 50 kPa or something like that out in the building? It is. Yeah. So at no flow, effectively, what you've got is down here somewhere, 50 kPa there, and you work from that point all the way up there. So from speeding up from there, slowing down from there down to there is a humongous decrease in energy. We're talking a couple hundred watts, and it's just ticking over. Although out here, it could be a massive amount. On glandless pumps, the older ones are old UPS pumps, now use magnet. They don't have a minimum flow. So you've got circuits that actually shut down, as in all the valves shut. If you're daft enough, you could let them just pump one because you just work against the closed valve head without overheating the failure. But not on conventional mechanically sealed pumps. In the data book, it does refer to these as having no minimum flow requirement. But you are limited in the size of pumps that are within that range. And to me, 5, 6, 7, 8 litres a second, up to 100 kPa maybe, that's where it used to be when I started in the industry. But you are finding 150, 200 kPa nowadays because of long runs, pipe work and so forth. If you can get them down to this area, not a problem. You have to worry about minimum flows. You still need a minimum flow to keep all that kind of stuff. And of course, if you get a decimal point in the wrong place, that can happen. If that lands on site, it ain't coming back. This isn't one of those, by the way, just I found it on the internet. So that is a real impeller on something in a power station somewhere. We do sometimes get people do calculations in litres a second, go onto a website and work in cubic metres per hour, so the pump's undersized, or they've worked in 2,000 litres a minute, size the pump up in litres a second, and it's gone. But they do sometimes come out. So just be mindful, pumps of that size do exist.
We should all be working to the SI, because those mistakes work in lots of systems, and all work in vent, and people are continuously using cubic metres an hour, and that's not the right figure.
I thought sleep on a cubic metre per hour.
Oh, it would for water, yes.
I was water gallons a minute.
But the problem there is if you're using metres or litres an hour, you are looking around with 3,600, and that's a silly game, because you're really just going back to the difficulties of imperial systems, because I'm sadly old enough,
So
and I have, and I still could design a gravity system.
Would you?
Oh yes, and that's all. I mean, but it's an annoying thing because people do make mistakes.
Oh yeah, yes.
It's computer says as opposed to.
Because everybody's in a rush anyway nowadays.
Absolutely.
You want to try working out long now and again, and you'll suddenly realise where you went wrong. But when the computer says that's the answer, that's it. Don't go back and work it out. Right. I've had enough. Sorry, gentlemen. Any questions? That question, I know it was a long-winded answer, but that is the most common question we get asked. Minimum flow rates.
Do you plot it against the inverters you chose?
No, we don't choose an inverter, we make our own. We don't go ABB, whatever. We make our own inverters. And that curve, sorry, that That one there is our own Grundfos inverter. That one on there is built into the pump, actually manufactured by Grundfos, not badged. We do badge separate wall-mounted inverters with their own controls on the front. That's actually Danfoss inside at the back. But pumps with inverters on, unlike any other manufacturer, we do not buy inverters on and bolt them into their pumps.
But the range has got so strong, hasn't it? You know, it was on the body of the pump.
Yeah, and what you will notice is pump speeds have gone through the roof. That pump there, that one there is based on a 2900 RPM pump, 340/2. That pump there, it's not shown up there, but that particular one will run at about 5000 RPM. I hear from people who are old enough to use belt drive pumps. Well, oh, look, wake up, smell the roses. The impellers used to be that big, they are that big, they're that much faster, that much more efficient. And they work. How many have got a domestic central heating system at home? Wet central heating system. All of you, maybe? Yeah. What colour is your pump? Red, blue, horrible greeny colour? If it's blue, I was involved in the design of it donkeys years ago. And if it's working, do that. And if it's red, it's a Grundfos. They're all variable speed drive with an inverter in it. I've got one in our place. It was originally 55 watts. When I have the heating on only, it's 4 watts. When I have the hot water on only, it's 7 watts. It used to be 55 watts. But as I say, so I've saved 40 or 50% energy, maybe even more, but it's only watts. You move that into 10,000, 20,000 pumps, it's a huge amount of energy. So we've done our bit to save energy, to stop them to keep making new power stations. And all these pumps here, the Glandis pumps years ago used to be 3-speed pump. Designers used to love them because you select on the middle speeds. If you cocked it up, you could always go up one or go down. With the variable speed now, you can do the same thing, but also talk to change the duty of the pumps. A lot of them now you can have variable speed, spin down from 0 to 10 volt, and turn it on and off while it's 10 volt, which we didn't used to do before. So we're leading the way with all the manufacturers and the old CPD. That's what makes them more expensive. We spend more money on this. That range, the Glandis Magnet range, I think £70 million as well. Now we've got it right for about 4 or 5 years. So keep Nigel happy, he's got a shed for them.
Has anybody done any research for, there you are, there's our wonderful technical pump, or pumps out there, and actually done research to see if they are set up correctly? So if you say, go and look at 1,000 pumps.
I'll see how many are actually set up correct.
And how many are actually set up correctly?
I would think 50%.
Yeah.
If
Poor, isn't it?
yeah. We're all men, we don't read instructions. You take it out of the box,
That's right.
stick it in.
We don't do
And
it.
that's why on this range we have what's all called auto adapt. You stick it in and you turn it on and go away. If somebody complains about the last radiator's not hot, you then go back to the fiddle with the pump. It sorts itself out and then speeds up and slows down and then goes up like a proportional curve, finds its way onto up here somewhere, and then slows down what it thinks is the best one. If you need a bit more, you just go along to it, press the up button. But don't press the up button until the top light's flashing because it's on maximum, you can't turn it off with the low voltage signal.
Because it's a shame, really, because we're putting in loads and loads of great technology and making it really cheap, considering what we're trying to do.
Yeah.
And we are not delivering it because the people out there who are maintaining it don't have the knowledge how to do it.
But as the old gits die off like us, the new guys come in and guys play on the phone. I mean, you can talk to all our electronic ones via your mobile phone with it.
Yeah.
Unfortunately, you haven't got a drive-by. So the guy who's bought the pumps and hasn't paid for them, I would like it is wireless. So you can rack up outside and dive into his pumps and just turn them off.
Yeah.
That would
Unfortunately,
be
the guy
nice.
who's in charge of looking after that, from a day-to-day point of view, sadly, in a lot of places, is only on 20,000 £.
Yeah.
you're going to get an upper for that. That's one of the problems.
Yeah. But a lot of this stuff now, you can network it and then send it to the cloud or wherever and sit in the office and it just flags up everything. It's all automatic. That's one of the downsides of having a fully automatic system. Because it's all automatic. Only when the whole thing goes wrong, does anybody go for us and
Yeah. So I was using your pumps in the early 2000s with lawn chips built in them.
Oh yeah.
So all my hospitals had them, and I was using all the data from those, and it was fully networked, and I was making those things work, so that if something went wrong, they self-diagnosed.
Yes. Yeah.
And so therefore, if computer says no, go do something, and if there is something genuinely wrong, you send the appropriate guy to go and do the job, i.e. the fitter
That's
or
how
the
it should be.
electrician.
Yeah.
There's no point sending the wrong guy, because your service is down. Your theatres are closed,
Yes.
and that's something I don't like.
Yeah. Particularly in theatres, never use twin pumps.
I
They're
know,
on the
and
table.
the little buggers always do.
Yeah. If I'm on the
It is
table, I
cheap,
don't have an operation.
but it's
I
not
don't have a
cheap.
twin pump failure.
Not for the bloke that's got to deal with the aftermath.
I think about Paul Hood on the table.
Yeah.
He's not happy. He's feeling quite cut up about it. But I had to make that joke.
Right, well, I'm done, gentlemen, unless you've got any other questions.
And I'm sure you're more than happy to stay around afterwards. For
Oh, I
anything
am,
that's,
yeah.
not
Probably
brave
been
enough.
for 2 hours, isn't it?
So just before we draw a close to this evening's proceedings, gents, if you wouldn't mind taking your smartphones out again, visiting menti.com, entering the code. What do you want to know about next? What can we help you to learn about? Knowledge deficits. And your future. We can get Howl up for Brexit again. Absolutely no problem.
Oh, not how. Oh, for goodness sake, I've just realised what you said. How many days you got?
Till Brexit?
No, if you bring Howell up
Oh yeah.
to talk about Brexit, you need days.
Oh yeah. Fountain of knowledge.
Shooting centres.
Funnily enough, 9th of February, 9th of January even.
There's a subject.
Just give you guys a couple more minutes or so. And then lastly, gents, some feedback if you don't mind. Helps us to tailor our events to suit your needs a bit better.
Excellent stuff. Thank you, gentlemen. Well, thanks, Steve. It's a changing picture, but you seem to have done all right. Just so you're aware, there's no seminar in December, but obviously we do have the annual dinner, so I'll be looking forward to seeing some of you there. Not a chance I'll remember you if you get me at the end of the evening. If you get me at the start of the evening, I probably will. The next seminar is on soft landings, which is one of the things that popped up there, on the 9th of January. So Steve's going to stay around for a few minutes while we pack up and put things away. If you've got any questions for him or myself, grab hold of us. And failing that, we'll see you on the 9th of Jan or at the annual dinner. Thank you.
Oh, no. I'm going to forget. About the booster dose, we were talking about on the module. Basically, he's got boosters. Yeah. We've got 3 or 4. We've got a sensor out in the field.
Yeah.
Up to the BMS, fill the BMS to our natural control across. I think what should be the way to put a sensor across the BMS to maintain, let's say, flagging. So I can't remember what the duty of the set. Let's say it's 2 doesn't matter. 250 capable of 20 litres. That's total 12 litres. Yeah, so 12 litres, so 2 to achieve that should be set. That comes back from the ordinance, preferably that should come back to our state, because that's the real data should have gone. If it's gone from the immediate state, that is the differential pressure transfer, which will to get 50, whether there's no wage will be more and more, we have to do 250. So there's not one now, there's now 10,000. It shouldn't appear we've gone from there direct to us, we've gone from there to the city. Well, so you go to the controls, then city, yeah, whatever. So the other way to do it is more differential pressure transfer. So you try to maintain 2 there. What you do is you want to turn the you vary the separate. So you pick your set, set to 250 kg.